Welcome. In this video, I will state and prove a theorem that I will call the fundamental theorem of quadratics. All right? As you may know at this point, a quadratic is simply a polynomial of degree 2. So it looks something like this. Has these three coefficients. And what this theorem states is that I can find the roots by the following formula. And I'll call them plus minus for a reason that will be apparent in a second. And you calculate that by taking minus b, this middle coefficient, and then plus minus corresponding to this plus minus, and then you take the square root of delta divided by 2 times a, where delta is calculated as b squared minus 4ac. All right. So this is the way you can find the roots for a quadratic. All right. The theorem also includes a statement on the vertex, and the vertex can be calculated as follows: minus b over 2a, which is the x-coordinate for the vertex, and minus delta divided by 4a. All right. All right. In addition to this, it also states that the sign of a, the leading coefficient in our quadratic, actually determines if the branches branch upwards or downwards. All right, and technically it also states that the a determines how quickly they branch either way, and that it's actually symmetric about the x horizontally about the x-coordinate of the vertex. All right, let's do it. The reason I have so many different statements in the same theorem is because it stems from the same proof. They just kind of branch it at the end, right? Okay, let's hope that this is in frame. It all starts by taking our quadratic there and dividing by a, the leading coefficient, because I want the leading coefficient to be 1 because it makes everything easy. Okay? So let's say that b of x divided by a is equal to x squared plus b over a x plus c over a. Looks uglier, but I believe that it makes things easier in the long run. All right. Now I do something beautiful that we do all the time in math. We add and subtract the same term. All right. We're not changing anything. We're just adding and subtracting something. So we do, and actually I extend this fraction by 2. So it goes 2 times b over 2ax. Looks weird, but there's a, as they say in Danish, meaning med genskabning. Okay, then I add something. I add this squared. So b over 2a squared. And then I subtract it again. And then I still just have my nice old c over a. Okay? The reason I did this is I want to use the quadratic formula for this. All right? I want to gather these in a single term. And what I get here is I get x plus b over 2a squared. And then I want to gather these two in the same term. I'll start by expanding this power, the square here, and the denominator will become a 4a squared, and that's what this fraction is missing. It's missing a 4a in the denominator. All right. So I say plus here, and it'll be yes, beautiful, and it'll be minus b squared plus 4 AC. So I expand this by 4A to have a common denominator here. Okay, so I have this in the number, and the common denominator will be 4A squared. All right. Yeah, beautiful. This is actually where it branches into the two branches of the proof. And let's start with the vertex. All right. So the vertex is a blue formula here. Okay. So I want to figure out where's the minimum or the maximum, where's the extremum for this quadratic here, okay? And if I look at this whole thing here, the only thing that varies is the term that depends on x, which is this one. This is technically a constant for a specific quadratic. So the only thing that varies is this, all right? The square. All right. I'm missing a last step here. I'm going to multiply the a over again, so we have our original polynomial, so we don't have some weird object. All right. And I'll notice that this is actually just a minus delta. I've just changed the sign on the delta. All right. This is actually just minus delta over 4a, because I multiplied by 1a, so it's not a squared anymore. And now we can almost see what's happening here. Okay, beautiful. Same argument. The only term that is that varies with x is this term here. Okay, the square is always positive. Okay, so this is the lowest value this can attain is 0. If this parenthesis here is 0, then it doesn't contribute anything to the polynomial, to the quadratic. All right? And that happens exactly when x has this value here. Then this does not contribute with anything. All right? Let's say it's not 0. Let's say x is something different from minus b over 2a. So this becomes some positive, non-zero number, right? If a is positive, then this will contribute something. Then this will increase the value of the quadratic. That means that moving away from this value, the value increases. And it's completely symmetric. If we move 1 to the right of, or if we increase this value by 1, we get one value. If we decrease it by 1, we get the same value. So it's totally symmetric about this value. And if the a is positive, then it's increasing horizontally away from the vertex. So that explains why when a is positive, it's a happy parabola. The branches are going upwards, and if it's negative, they're going downwards, because then the product of these is negative, because this is always positive. Beautiful. So that is the argument for a, the leading coefficient, the influence that has on the parabola, and the vertex is exactly when x is equal to minus b over 2a, because then this is 0, but then this becomes our y value of the vertex, which is exactly what the blue formula states. Wasn't that easy? Anyway, let's do the one where we find the roots. Right? When we're finding the roots, we need to find the values of x where the quadratic is 0. But the value of the quadratic is 0. All right? So we put a 0 on this side. But that actually just means that these two are equal. This is equal to this. All right? So let's actually rewrite that as ax plus b over 2a squared is equal to delta over 4a. All right? I will move the a back over to this side, because what I'm going to do now is I'm going to isolate x. All right? The next step in isolating x is actually to take the square root on both sides of this equality, right? So we have x plus b over 2a is equal to plus minus the square root of delta over 4a squared. And you can already see it's starting to look like what we wanted, okay? All right, so x is equal to minus b over 2a plus minus, and what we can do with the square root is we can take the square root of the numerator and the denominator. All right, so that will be the square root of delta, but the square root of this thing is actually just 2a. And these guys already have the same common denominator. So this becomes minus b plus minus square root of delta over 2a. All right, wasn't that beautiful? So the meat of the argument is simply this rewriting this thing, and the two results, two pretty broad results, actually just kind of fall out of the sky when you've done that. When you've done this rewrite, once you've rewritten the polynomial like this. Furthermore, this is actually something I'll call the vertex form of the polynomial, while this is the normal form. Yes. At the very end, I want to, since I have feels like I have some time, I want to actually add a statement. And this statement is that this polynomial has a third form, and this form is that you can write this as a times x minus the, what are the roots? Times x minus, the second root. I hope you can see this. Yes, all right. And how do I prove this? Well, I prove this by simply putting in the two roots I've already found and showing that this is correct. So, that's what I do. I take a times x minus that thing, minus b minus square root of delta divided by 2a, and I do x minus b plus square root delta divided by 2a. All right? Wonderful. All right. Common denominators, I don't want to do those fractions. Fractions are annoying. We all agree on that. And so I multiply this by, expand this by 2a, and multiply that and put it outside the fraction, or outside the parentheses. Okay, so what I end up with here is I end up with a divided by 4a squared, and then it's just x plus b minus square root of delta, and then x plus b plus square root delta. Well, this is wonderful. We have another square formula, square rule that says that when you have the product of the sum of two objects and their difference, you can take the difference of the squares. It's maybe sounding a little weird. Let's cancel these also. So it goes 1 over 4a, and then it goes, I take x plus b squared, and then I subtract the square root of delta squared. But that just cancels the square root. It's so beautiful. And these are actually equalities all the way through. All right? All right. So let's expand this. So we have 1 over 4a, and then we get x. We use the other square rule, x squared plus 2 xb plus b squared, and then minus the discriminant, but I can just insert that. So that's minus b squared plus 4ac. Oh, we're so close. Can you feel it? Oh shoot, I made a mistake. When I expanded this by 2a, there's actually supposed to be a 2a here. And that, of course, haunts us all the way down through all our calculations. So this is actually not just an x squared. This is actually a 4a squared x squared. And this is not a 2x. This is a 4a xb. All right. That wasn't that bad. People make mistakes. Nobody's perfect. Anyway, this cancels with this. And then we can actually divide the whole expression in the parentheses here by 4a. Because look what happens. Well, this cancels with this and this, this and this. And what's left? Well, we have an a left here. We have a bx left here. And we have a c left. Exactly what we want to prove. So at the very end, I add this little statement on the factorized form of the polynomial that follows directly from this red formula for the roots. That wasn't that bad. If you have any questions or comments, feel free to leave them in the comments appropriately, and I'll see you sometime.